Yep.
The van. You're in the van. In the van. Actually, the test, the storm was, that average was what I expected. It was a very easy test. I expected a pretty high average, and I should die. So, I'm glad. Anyway, let me go through this with you. Work along with me. All right, so first problem I had, this is all Z transforms. This is problem one. First one was x of n equal to n times 1/3 to the n u of n. And for this one, I'm just going to talk my way through it. First thing I say is 1/3 n u of n is something we should know, and that goes to simply z over z minus 1/3. And I'm going to leave it like that. It could be 1 over 1 minus 1/3 z to the minus 1, but I'm going to just leave it like this. I think we know we can divide top and bottom by z. So if you have that, that can look like an x of n here. Just assume this is x of n is generic. Then if you have n times x of n, that goes to simply, it's going to be minus z times the derivative with respect to z of x of z. When you go ahead and do that, I can do this for you. And then you're going to get finally, when all is said and done, you're going to divide by 3. Now, let me do it this way. That'll just break out as z over 3 over z minus 1/3 squared when you do the derivative. So that's the answer for the first part. I believe it's A. Part B was x of n here would be equal to cosine of pi over 3 n times 1/4 to the n u of n. Here, I'm going to, now people, most people got these things right, but there were probably 4 or 5 that they confused these with the sign, and I want to do this once and for all. Remember, you got to know sine and cosine times any functions, both in the time domain and the end domain. You've got to know this, because you're going to see it on the final, I'm telling you. You have to know these. So for this one, it's pretty simple. If I have simply 1/4 here, to the n u of n, that goes to z over z minus 1/4. That's how I'm going to do it. If you want to divide top and bottom by z, you can, but I'm going to leave it like that. Understand? Now, when you have the cosine modulation, this is like the x of n. So if you have any x of n times the cosine, in this case, pi over 3 times n, what that does is always break a half out. And then you take the original function here, and the z is multiplied by e to the j, and really it's going to be omega, right? And the omega is going to be the pi over 3. Is that class? Times, is everybody with me? So now you're going to have a z times e to the j, and this is going to be pi over 3 over z times e to the j pi over 3 minus 1/4. This is one way to do it. And then it's going to be plus z times e to the minus j pi over 3 times z e to the minus j pi over 3 minus 1/4. And you got to have the half in front of that. I'm going to leave it like this. If you wanted to go ahead and get a common denominator and combine all that, it's fine, but this is the modulation I expected to see. People did combine that. Somebody, did you do that, Josh? Did you combine it down?
I used the property z squared minus CA.
Yeah, you can do it that way, but this is just as well. Yeah, that's fine if you did it that way. So this is, what-
Do you want to do it that way? Can you do that way?
do what?
Can you do it that way?
Yeah, you can do it that way.
No, I mean, can you do it that way?
Well, you just put up the formula. What he's saying is if you have, it would be z squared, right? And then it's gonna be what?
Minus CA.
It's ZA here, or AZ, over, then it's Z squared, minus 2AZ plus A squared, I think is the one you're using, is that?
There's some cosine terms.
Right here. There's a cosine, sorry. And this would be the cosine of pi.
There's some cosine in the top AC.
Yeah.
Yeah, sorry about that. And it's going to be plus a squared. If you want to do it that way, you can. You just plug in the cosine. It's going to be the cosine of pi over 3. Cosine of 60 is 1/2, right? And then you can put that in there, and you'll get the same effective answer. And if you did it that way, it's fine. I don't know. I didn't know. I thought only you did it that way. Did you do it that way?
Yeah, I tried to.
All right. Well, then this is going to be 1/2 right here, and this is going to be that's going to be 1/4. Right? And actually, yeah, there's a 2 here, 1/2, 1/4 times 2, so it's really 1/4. But that'll do it. And your A is going to be 1/4. That's fine. Almost everybody did it that way. And for part C on this one, this is x of n is equal to, let me go here and do this. You see the erasers to this board anymore? That's all right. Well, this one is x of n, part C, equal to u of n minus n u of n plus 1/3 n times u of n minus 1. And for this one, I'm just going to, a lot of ways to do these things, by the way. I'm going to show you the way I'm going to do this. I'm going to go down here and simply put this as z over z minus 1 and be done with it. Now the second one, the u of n is my x of n. U of n is like x of n goes to this. Therefore, n times u of n is the derivative of this with respect to n. Yes?
I just have a question about that one, I could wait. But like, what I did on that one was I brought the like e to the j second part.
Would you do me a favor? If it's a specific question about your test, could I look at it afterwards?
I have a few questions.
That way I'll take care of the specific questions afterwards. These are generalities. So this one goes straight here. Now, minus n times u of n, right? That's going to boil down to when you take a derivative of this and multiply times minus z, you end up with minus, and it's going to be, and this, the way I left it, it's just z over z minus 1 squared. I know some people combined it and got a common denominator here. It's fine, as long as that's how you're doing. Finally, for this one, the last one right here, I'm going to suggest the easiest way is to take a 1/3 out here and make this n minus 1. Now, you didn't have to do it that way, but that makes it easier. So if you do this, then I just make the point that 1/3 to the n, u of n, is like an x of n here. And that simply goes to z over z minus 1/3. And then if I have x of n minus 1 here, that's going to bring out a z to the minus 1 in front of it, times this, z over z minus 1/3. And So there's a third out in front of there, that brings the third out in front, and then you're left with simply, and you can leave it as just 1 over z minus 1/3. Now, if you there's a lot of fancy ways to do this. You can get a common denominator here. You can do several other things, but this is the easiest form of the answer, and I checked the answers. All right, now if you got something or you think I didn't grade fairly, see me afterwards. But that was part C, and part D was I gave you x of z was equal to z over 8z squared minus 2z minus 1. And I know that is coming from some x of n. So then I just asked for n times x of z. And I wanted that. And this just meant you had to really actually use the property, not memorize formulas. So for this one, the property here is going to be minus c, right, times the derivative with respect to z of z over 8z squared minus 2z minus 1. Everybody okay with that? I'm just literally using the definition. I put that in there to make sure you knew the definition. Because some people never show me work, they just show me an answer, and I don't know what in the world they're doing. So now you have to do some work to get this one. To get this one, it's minus z here. Then the derivative of the first is 1 over 8z squared minus 2z minus 1. Then it's going to be minus 8z squared minus 2z minus 1 squared. There's a z up top already. Then I have to take the derivative of this, which gives me 16z here. And then it's going to be minus 2. Are you with me so far? Now, the next, you get a common denominator. And then you finally take this 8z squared minus 2z minus 1, put it here, and I'm going to do it. Well, I'll do it underneath. So I have z times, then I have 8z squared minus 2z minus 1, minus the quantity 16z squared, and then plus 2z, all over 8z squared minus 2z minus 1 squared. Here, we're going to combine terms. So I see the minus 2z plus 2z going away. Right that. And then I have minus 16z plus 8z, or minus 8z squared. And then I have a minus c in front of there, goes through, makes this plus, makes this cubed, makes that plus, makes it z. And that'll be that form of the answer, one form. There's several forms. This is one form. Okay? I just collapsed everything. Are you all right with this, everyone? All right. Then, that's it. Number 1. Number 2. What is DTFT? And I gave you x of n was equal to n times 1/4 to the n u of n. Now, for this one, if you knew enough, you could use the z transform property and just turn z into e to the j omega, and a lot of people did that. And that's probably the easiest one. But you can use the actual property and say, well, for this one, I'll just do this. 1/4 to the n u of n. That goes to what? It can go a couple ways. It can go to what? E to the j, right? J omega over e to the j omega, right, minus 1/4, that's one way to do it, correct? I could divide top and bottom by e to the j omega if I wanted to. And if I did, I could say that's equal to 1 over 1 minus e to the minus j omega divided by 4. That's another way, it's completely legit. Now if I have n times that, n times this is like a quote x of n here, n times my quote x of n. That means I get a j times the derivative with respect to omega of that 1 over 1 minus e to the minus j omega over 4. And that brings me to j, and then I have 1 over 1 minus e to the minus j omega here over 4 squared. There's a minus sign here, and I have to take a derivative of that with respect to omega, so I get another minus no, actually it's plus 1/4 times j times e to the minus j omega, right? And that means I'm with 1/4, the j's are going to go to minus 1, there's a minus sign, makes it plus, times e to the minus j omega over 1 minus e to the minus j omega over 4 squared. And some form of the answer. Now, if you multiply top and bottom by e to the j2 omega, then this becomes positive, then there's an e to the j omega here, and there's minus 1/4 here. But any answer is correct, either one of those. The next one was this problem, the DTFT, or I wanted the inverse DTFT of this. And this was one we actually worked on in class. This is minus pi over 2, pi over 2, 1, and then I have this 3 here. And this is my x of omega. I'm going to put this down over here. So for this one, first I'm going to define it in terms of standard functions. I'm going to say this is really a pulse function of width pi in omega of height 1, plus a triangle function of magnitude 2 of pi, with pi, a triangle function. Now, some people remembered the exact inverse transform. Some people didn't. So I'm going to go through it. And remember, this is the one where we can use duality because it exists between minus pi and plus pi only, right? So we can easily use duality. That's the whole thing with duality. So I'll show you exactly up here how it works. Do you remember doing this for homework, this problem? So for this problem, first I'm going to start with the general formula. For a pulse of with tau in the time domain, it goes to tau times the sinc of omega tau over 2 in the frequency domain. Now, I go ahead and use duality, and that comes tau, and then it's sinc, right? And now it's t tau over 2. Duality says that I have to take a 2 pi here, and I have to put where the pulse here, tau, and t is replaced by minus omega. Because it's even, I can plus omega. Now, before I put a small omega in there, I'll make the argument it's the same thing as large omega because we're using the characteristic that the actual, if you've got an inverse transform with small omega to time, and it's between minus pi and pi in the omega domain, then you can simply say it's the same thing as the large omega, right? Transform, and instead of t, you get n. Do y'all remember this class? So I don't have to babble about it too much. So now I'm just going to say this is the same thing as capital omega here, and then I'll divide this by 2 pi on this side, And I'll replace T with N. So I have this, because this is what I need. Okay? I'm just going ahead and doing the replacement. Then after that, I do the triangle one, and I'll do that right here. For the triangle one, I get this. Triangle function, tau of T, goes to tau over 2 times the sinc squared of omega tau over 4. We use duality. Now this is tau over 2 times sinc squared of T. I'm going to go ahead and put in N. N tau over 4. Here, I'm going to get the 2 pi times triangle function here of tau and capital omega. Small omega first, actually minus omega first. Because it's an even function, I can make it small omega. Because it's between minus pi and pi, I make it large omega, because I know I'm going to do a dt of t. Then I divide by 2 pi here. And now I have that. So now I have my base relationships that I need. I have the transform for the pulse and transform for the triangle in the omega domain back into the end domain. Now I just weigh them accordingly. The weight on that one in front of it, the weight as a coefficient is 1, right? For the pulse, and the actual width is pi, so tau is pi. So that means this goes to simply 1/2 times the sinc, and then it's n times pi over 2. Right? Now it's plus 2, the weight here is a 2, so the weight here would be 2. Tau is pi, so it's, that's 4, I'm sorry. There should have been 4 here. There was a pi, or there was tau over 2 first, and there was 2 pi over there, so it should have been 4 pi down here. Sorry about that. So that's going to be plus 4 pi below, and then we have a width of pi, so I have 1/4, but it's times 2, so it's 1/2. Now it's times the sinc squared, and then it would be of n pi over, because tau is pi over 4. And that's it, that problem. I think that's just about identical to the homework. I even think the weighting's the same, if I'm not mistaken. All right, that's the second problem. Third problem. You know, we're playing Liberty, right? Did you know they beat Troy? It may not be that easy of a game, is what I'm saying. I'm not liking what I'm hearing. I didn't look at the handicap on that one, but there's something very unsettling about a tune-up game being a troubling game. Anyway. For this one, first we get the transfer function for this. I'm gonna tell you that this is a simple feedback loop. It's positive feedback. One way to look at this, and I'm just going to show you this, is I can make it negative feedback. I can make that minus and make that minus, and now it's negative feedback. It's just the coefficients, right? So it doesn't matter the form, as long as you know your feedback equations, now it's negative feedback by changing the sign there, isn't it, class? If you do this, this whole section can be replaced, the section I have blotted there, by the function forward gain, or z to the minus 1, that's your forward gain, divided by 1 plus forward gain times reverse gain. Because the reverse gain is a minus a, it's going to be minus a z to the minus 1. Forward gain is always going to be the gain as you're going forward, z to the minus 1. So now I can take that, and it doesn't matter how I do this, but I can go ahead and multiply top and down by z, and I have 1 over z minus a. It's still the same thing. You all agree with this? Right? Not very true. So then I can just erase this. I'm going to erase it. And now I can replace that whole section by 1 over z minus a here. Right? Now, it wasn't meant to be tough. The only thing you have to do is, and you could have done this in several different ways. And this is now going to be an x of z that comes in. And this is going to be a y of z. Y of z. Now, if I look at y of z by definition, now I really have what? I have two things in parallel, but the weight here of the parallel segments is just 1. And I have 2 in series here that I multiply together. And I take this one plus this one times my input function, I get my output. But really, y of z here, you can reason it out. It's a, right, over z minus a plus 1 times x of z is equal to y of z. Does everybody see that? If you do not see that, please come and talk to me afterwards. This should be very apparent by now. Those two, a and 1 over z minus a, are just multiplied together. They weigh the actual x of z going in. It's added to simply x of z. So I can factor out x of z and put a 1 here. Now, that becomes what? I have z minus a as the common thing, and then I have z minus a plus a here, times x of z, or then I have y of z divided by x of z here is equal to my h of z. That was the bottom line, and that can be rendered as simply z over z minus a. Now for that one, if you remember, the whole thing is, whenever we had this kind of thing, it had to be something for the actual stability criteria. For it to be stable, the poles had to be inside the 1 circle, right? So if you take a look at this, where are the poles? Where they're at what? Z equals A, correct? And that meant the poles had to be z less than 1. Do you agree with this, class? The magnitude of z had to be, or I mean less than, it would be less, magnitude of a less than 1. And I'll show you what I mean by this. Magnitude of a less than 1. And the reason I'm saying this in a complex z plane, where this is the real part, and this is the imaginary part. If I come out here and draw the 1 circle, and I look at where the pole of this is, the pole is going to be z equals a. So if this was distance a magnitude, here's the pole. That pole has to be inside the 1 circle. So that means a has to be less than 1. And some people did, and they did a greater than minus 1, less than 1. What they didn't do is put minus j here, less than, or plus j here. They didn't get the true idea of a magnitude, but I gave it to you. All right. It has to be the magnitude of a, because a can be, remember, it can be 1 at an angle of 50 degrees, or less than 1 at an angle of 50 degrees. Here, it can be anything. It can have a real and imaginary part. It isn't strictly real. That's the thing you got to be careful about. But the magnitude of a less than 1. And I know some of this is a little still real obscure. Well, how does this translate into the actual time domain solution? We'll get there. I know we have a couple of last classes left, and all this stuff I'm going to flesh out for you. Just realize when we're in the Z domain, those poles have to be inside the one circle for our Z transforms, just remember that. So that was that problem in a nutshell. Next, after this, we had, last problem. Oh, so I gave you x of omega equal to 1 over 2 plus e to the j omega. And then I asked you some things. The first one for A was I wanted the transform of x of n minus 5. This is the simple shift property. Shift in time, phase, and frequency. It doesn't matter if you're in time domain or n domain, t domain or n. So this is going to be simply equal to e to the minus j, the 5, and then omega here times that, times 1 over 2 plus e to the j omega. That's all you had to write down. Part B, that's a simple property, was n x of n. Again, you're using the derivative. You're using multiply by n here. It's a derivative over here with respect to omega and a weight in front of it. Right? So here, you're going to get j times the derivative with respect to omega of 1 over 2 plus e to the j omega. And when you do that, you end up getting e to the j omega over 2 plus e to the j omega squared. It's a straightforward thing. Remember the derivative, this is where people messed up. The derivative with respect to omega of e to the j omega is j times e to the j omega. It's not j. All right? Remember that. That's, people make mistakes there. All right, then part C was x, I had x of n minus x of n minus 1. Forgive me. Now it's okay. So for this one, you can actually do this a few ways. I'm going to do it the simplest way. X of n goes to that. 1 over 2 plus e to the j omega. A delay of 1 simply brings out, and it's a minus, it's going to bring out the actual e to the minus j omega times the original, or divided, or times 2 plus e to the j omega. When all is said and done, you can write it as simply 1 minus e to the minus j omega over 2 plus e to the j omega. I didn't ask you to do a filter property or anything like that. That's as simple as it got, and that was correct. Finally, I said x of n times cosine of 4n. And for this one, the only thing you have to do is the cosine property. But now, you remember you're in the DTFT, you're not in the Z domain. So for this one, it goes to 1/2, and it becomes, you take this property over there, or 1 over 2 plus e to the j, and now it's omega plus omega, not a 4, plus 1 over 2 plus e to the minus, or e to plus j times omega minus 4 here. And that's sufficient. If you want to combine them into a common denominator, you can, and get that, but that is absolutely easy. I was looking for properties and all these things, and I wanted to make sure in this one you knew you're adding it to the exponential. With the z, you're multiplying z by e to the j 4, right? That was the difference. but it's, they're the same thing. So those are all those things. I think that was the last problem.
Yeah.
That's it, and it was very straightforward, very simple. Wasn't in any way, shape, or form to be confusing or double. That's it. Now, I know Thanksgiving is upon us, so I'm gonna tell you what we're gonna do. Next time you come back, we're gonna finish some windowing stuff. I'm gonna give, we got like 3 class periods? How many class periods do we have? 3?
4, 5, 6.
We have a full 6 periods?
Yeah.
Fantastic. All right, we'll get through windowing, and we'll apply windowing, and we'll do some Z-transform stability stuff too. And probably, if we have a full 6 periods, I didn't realize it was that many.
Yeah, we go until
2 weeks.
7.
No, this is perfect. I can cut through some stuff that I've been waiting to get through, and I've always had trouble with this class, but that's perfect. And what I'm gonna do is, over breaks break, I'm not gonna do anything over Thanksgiving. If you're smart, you'll probably do a little review, but windowing is something we're gonna be doing. It's in the book. I'm also, if you look at the next chapter that has windowing in it, some of the filtering techniques I'm gonna talk about, and I'm probably going to give you at least one MATLAB assignment when we get back, and then I'm going to ask you to do yourself. It'll be a little more challenging. And we're going to have, let's see, at least one more quiz, possibly 2 more quizzes that'll be on the new stuff. Windowing is real important. Yeah.
Is for the final exam, is windowing the new
The stuff on windowing that would apply can't be programming. It has to be something that would involve the expected waveform outcome. And I'll show you ways of getting a close estimate that I didn't have time to. You know how, when you think about it, pulse goes to what? Sync, right? And frequency, right? That's very similar to what? When you saw a finite number of pulses, right? Without any kind of a weight on them, right? Not sampling something. What did it go to? Something that looked like a sync function to it. Do y'all remember that? Yeah. So for a large number of pulses, we can effectively say a sync function can mimic it. What do you think happens to a triangle? Looks like tau over 2 sync squared of omega tau over 4, right? And I'm going to show you parallels, approximations that you can do for the windowing. Now, with something like the Hamming window and the Hanning window and the Bartlett's window, well, Bartlett's is triangle, I'll show you ways of getting a close approximation, at least in my opinion, that you can estimate things. I'm not going to ask you to do any programming on the finals. I know some teachers ask you for MATLAB programs or writing C code or something like that. You're not going to get that from me. All right, it's all going to be based on the homework I give you. All right? So have a great break. Drive safely. The state police know you're coming home. And